Hey everybody, thanks for coming to the ITC Colloquium today. We've got Jason Hunt visiting us. Jason got his PhD at the Mullard Space Science Lab at UCL with Daisuke Kawata. And then he continued working on the Gaia mission for a little while after that in the Data Processing and Analysis Consortium. He moved to Toronto for the Dunlop Fellowship with Joe Bovey, and then to the CCA, the Flatiron Institute in New York. He's been at Surrey for the past few years, and he has done some great work on the structure and dynamics and history of our galaxy. So please take it away.
Okay. Great. Thanks, Scott, for the introduction. Yeah, very nice to be here. Thanks for the invite. As Scott said, I've been at Surrey for the last couple of years, first as a research fellow and now finally as junior faculty. So it's exciting to be stable at last. And
can we slide the podium across so we can see
a little precarious out of the way? You good? Cool. So yeah, I am mostly a Milky Way or galactic disk dynamicist or chemodynamicist. And so I'm here to talk today about the ways that our galaxy deviates from that traditional equilibrium disk. So ridges, ripples, and spirals across the Milky Way. I always like to start with a little bit of perspective, right? We know we live within a barred spiral disk galaxy, and we have this pretty well-known artist's impression here on the right. It is based on real data from GLIMPS, but of course we don't have this view. We can't go outside. We can't look down upon the disk. And so while we know we're a barred spiral, the exact parameters, the exact properties of the various structure within our disk remain somewhat uncertain. We know we have this central bar, but the exact length is unknown, the exact mass contained that is unknown, pattern speeds, that's the rate at which it rotates is unknown. And I would say the spiral structure, potentially even more uncertain, depending on who you ask. Again, we think we're a spiral galaxy, but the number of arms, their nature, whether they're density waves or materials, or even tidally excited by a satellite, is not fully solved. And it's because we cannot have this global picture. Instead, we have this view from the inside, right? We look up at the night sky, we have this wonderful, beautiful band of Milky Way across the sky, but you are then plagued with selection effects owing to our location within the galaxy. We have stuff like dust extinction obscuring a large number of the stars, and any survey selection effect inherent in any survey, whether from pointings or sensitivity. However, there are also real advantages to our position within the Milky Way, right? This is the only system where we can explore 60 position and motion of stars up close to explore how those dynamics works, the effect of the bar, the effect of the spiral arms. And so we always need more surveys to push further into the Milky Way to give us more stars, more data. But we also need simulations and models to help us really interpret that data. For surveys, we had the Gaia mission. As Scott mentioned, I was involved in this briefly just after my PhD, but one of the European Space Agency's cornerstone missions supposed to map originally 1 billion stars in the Milky Way and cost $1 billion. So the tagline was like, for every dollar spent, you get a star's worth of information. And fast forwarding about 10 years, we've now mapped around 1.8 billion stars in the Milky Way, and Gaia was mostly on budget, so we did better than expected. Also, it is now finished. Gaia basically turned off earlier this year, which is a great shame. However, we still have only processed about half the data it collected, so we're going to get new Gaia data releases for the next few years. Gaia is primarily an astrometry mission, measures positions on the sky and then extrapolates proper motions and parallaxes from that. So it's very well complemented by ground-based surveys such as SDSS, other spectroscopic ones that can give us more radial velocities in chemistry. Gaia does some of that, but a much more limited subsample for the radial velocities in the chemistry. So here's like the brief infographic of what Gaia made for Gaia DR3. This is the last one a couple of years ago. We'll have DR4 December, the end of next year, where things will get even more exciting. But so yeah, 1.8 billion stars overall, of which 1.5 have object classifications, astrometry, and photometry. And then you jump down a little bit to the spectroscopy, very low resolution spectroscopy for a few hundred million, which is still a very large amount of information, but they are very low resolution. And then high resolution spectroscopy for some smaller number of millions, and radial velocities for 33 million. So the radial velocities complete the 6-dimensional of phase-space information velocity towards and away from each other. And so that's mostly the sample that I'm interested in and will be working with in this talk. If you don't care about galactic dynamics, Gaia has also been great for binary stars, solar system objects, and some galaxies further away. But anyway, as I am a disk dynamicist, the thing that I've been most excited about is how Gaia has helped reveal the structure of the solar neighborhood and the galaxy beyond. So again, I'm going to use this artist impression infographic here on the left to give us the rough range of what you see. So the sun would be there, and within this kind of bubble in Gaia DR2, the first significant data release from Gaia, we could start to map the kinematics of stars out away from the sun. And so this is a map of the radial velocity, so motion towards and away from the galactic center in the solar neighborhood. Red are stars moving outwards, blue are stars moving inwards. So you can immediately see this is not a smooth, perfectly stable system. Not everything's going around nice in its circular orbits, but you have your outwards moving stars in red, your inwards moving stars in blue. You can say maybe qualitatively it might match where we think some of the spiral structure is going on. Jump forwards. Gaia is well complemented by the ground-based surface, as they said. This nice map by Christina Eilers from over at MIT from 2020. We can now see this red arc of outwards moving stars is a lot more extended. You'll also see that we flipped to be on the other side of the galaxy, that we've not moved anywhere. It's just changes in preferences in coordinate systems, etc. But we have now a larger volume around the sun. We can start to reveal these. Again, they look like qualitatively they might match the spiral arms, which is what Christina predicted in that paper. And then just this one as well, a couple of years later, also from Christina. I love this map where now the arrows are showing the motion of the stars. So you can see this kind of large scale rotation. You even see a slightly boxy feature in the middle, which is the bar. And the color is the chemistry. So red is more metal rich, stars in the inner galaxy. Blue is more metal poor, stars in the outer galaxy. That all makes sense. That matches what we know already about the galaxy. It's not new, but it's a beautiful illustration that we can now just make by just plotting the data on the plane. Right? We've reached that kind of regime. And then the other dimension, which you can't see in the face-on value, is that these stars are also moving up and down. So in that same paper with Christina, again, now red is stars moving upwards and blue are stars moving downwards. So not only do we have those large-scale radial velocity features that might correspond to spiral arms, we have something similar in the vertical velocities, and that doesn't come naturally out of such planar structures such as the bar and spiral. So this is a little bit fuzzier. It's not as well defined, but you can see the transition between this upward moving band from like just outside the sun, and then about 15 kiloparsecs, you have this blue band of downwards moving stuff. And so if you put all this together, wrong way, sorry, we're looking at these ripples in the disk. So there was this paper from Eloise Appoggio fairly recently this year talking about the great wave, so something like propagating outwards through the galaxy. And this is one of the illustrations from, I think, one of her media releases that I just think is beautiful and shows nicely what's going on, right? As you go out from the galactic center, like the image in the background is not the Milky Way, obviously, but the arrows of the data are. And so you can see effects of, yes, go ahead.
Is it clear who is the perturber? Is it?
So that's going to be a large part of the focus of this talk. So there are obvious candidates, but the spoiler for the end is it's not fully solved. We have ideas, but it's not guaranteed to be known at this stage. So, and a lot more detail will be answered over the next 45 minutes today. And this in itself is not an entirely new thing. It's not that Eloise has just discovered this now. It's this also had this impression all the way back from 2009 from Heidi Newberg's group, where by seeing like Monoceros and Triandromeda being above and below the plane in the outer disk, you could kind of infer that there is this kind of ripple structure going on. Originally, people thought they might be disrupted satellites, but actually chemistry and everything, proper motions match and being outer disk structures. So they put together this image and this picture a long time ago. But now with Gaia and complementary ground-based surveys, we can fill in the rest of it and see that they are really these large-scale ripple structures. But also just to mention here, the artist always had it going up where it's the spiral arms and down in between. That's not true. That's not true. They don't correlate, but I still like this image for the general impression of these ripples on top of the large-scale S-shaped one. And you can also see these ridges and ripples in other projections. So if you look, these are two papers actually submitted on the same day, right after Gaia DR2, one from my group, one from Trezer and Toha. If you plot the position of stars as a function of galactic radius, R versus V phi, so that's the speed of which they rotate around the galaxy, you get all these like ridge features in this direction. So Daisuke linked it to potentially spiral arms, Trezer to potentially do galactic bar resonances. And these are actually long extensions of long known moving groups in the solar neighborhood, which we now know stretch across several kiloparsecs. So for example, this old picture of the moving groups first discovered by Olin Egan. This is the well-known Hercules stream, and these other moving groups, Hyades, Pleiades, Cambrides, Sirius, correspond to the ridges in this picture. So Hercules would be this one down here. Sirius is this long one here. And so they're not local features, they're large-scale dynamical features. We also discovered striking spiral patterns in the vertical position versus the vertical motion of stars in the solar neighborhood. So if you take a little 1 kiloparsec box around the sun, plot on the x-axis vertical position z, and on the y-axis vertical velocity vz, you might just about, or depending on the contrast of objective, maybe you can't see in the density, it's close. There's this faint spiral pattern that goes up and down around. In the rate of velocity, there's something in there. But if you then paint this image by azimuthal velocity, it really pops out there into the striking spiral pattern. And this is some indication of incomplete vertical phase mixing. So again, something has made the galactic disk ripple, and they're all mixing back towards the equilibrium state. And we can form all of these features in simulations to help us kind of examine where they come from. Helps us, as I said, compensate for observational biases, look at evolution from time, scales we can't see, but they're not truth. All simulations are wrong. We just have to use them for what they're good for. But we can kind of see how these things evolve and propagate over time. So as illustration, ridges in RV5 can be made by bars. Mentioned that as this M-body model from Francesca Franguti, where you get ridges in the density and a distinctive pattern in the radial velocities for the stars moving in and out. And I like to highlight this because a lot of people use these features then to try and measure the pattern speed of the bar. Because if you can assign the correct bar resonance to the correct feature, you know how fast it's going for it to be in that part of phase space. However, these ridges can also be made by spiral arms. So there's, again, there's an image from the, plot from the Gaia data for one of my papers on the left, Gaia plus apogee, and you see all these ridges. This is reality. This is just a random model with some spiral structure. You get all the same kind of ridge features, but there's no bar in that model. And if you have one or the other, you can do this kind of measuring of bar pattern speed from the ridges. So this is quite an old animation now from a former undergrad of mine, Matthew Bubb, but I still like what it shows, where you have a smooth disk, nothing going on, you have no ridges in the space. This is the view colored by radial velocity. And then if we turn on the galactic bar slowly, you'll start to see a resonance feature appear around here. There you go. So that is the outer limb-bud resonance in this image. It's nice and clear, and then you can measure how fast the bar is going from it. However, if you also have spiral arms, which the Moke does, if we turn them on now, suddenly everything gets a lot more complicated, right? So we know we have spiral structure. This is more qualitatively what the Gaia data looks like. We know, because we set up the model, that this feature here is the bar resonance. However, if you don't know that, and you pick the wrong one, you're going to measure the wrong pattern speed. So there's a whole slew of papers in the literature measuring bar pattern speeds from these kind of data points. However, they all find different answers, and all of them make different choices in what they choose. However, in this illustration, even if you choose the right one, you're actually off by about 5 kilometers per second per kiloparsec, because the spiral arm has come by and dragged everything a little bit off. So this is just a little bit of a cautionary tale for how easy this is to do. And then this is further complicated by the fact that these ridges can also be made by satellites. So coming back again, whatever has potentially caused these ripples across the disk, you have a dwarf impact the galaxy, you again spread these ridges across the disk, across the space. There's another realization of the Gaia data from Chevron Laporte and his M-body satellite model. So they're not a quantitative match, but qualitatively you get the same behavior. And the satellite scenario here is kind of appealing because it also makes the phase spirals, right? Something does that vertical perturbation and does that incomplete vertical phase mix, and you don't get naturally from the bar and the spirals. And so this is the very old, well, not very old, 2019, 2017, M-body model of the satellite merger from Chevron Laporte. He doesn't get anything in the density, it's too low resolution. If he colors it by azimuthal velocity, you start to see these same features pop out, but they're way fuzzier, they're not as well refined. And that's because we've now really entered a regime where we have so much data from Gaia, we have so much more resolution in reality than we can do in even state-of-the-art simulations. This one is now a little bit out of date, 5 million particles in the disk. So a few years ago, I ran something at 1 billion particles, which is still not enough. We're still a couple of orders of magnitude below what we can see in Gaia, but it does help examine the dynamics in more detail. So just to show it, I'm going to play this movie. Hopefully it comes out after Zoom. The surface density of the disk here, radial velocity pattern, that's edge on disk density. This would be mean Z, so position above and below the disk plane, mean VZ, so the velocity is moving up and down. And then this bottom panel, you'll see the satellite disrupt when it comes in. And so I throw a satellite at this disk. Okay, so the galaxy settles a little bit in the beginning, but there's nothing going on. This is very smooth and stable. This is an idealized disk. It's not Milky Way-like. It's designed to be stable until the satellite comes by, and there it is. So you get these large-scale ripples in the radial velocity and in the vertical dynamics, right? So you have these little rings and ridges similar to what we see in Christina Eiler's and Eloisa Poggio's data. And every time that satellite comes through, you introduce distortions and ridges and ripples on top of the ones that were there. And as it gets further and further, everything becomes a lot more complicated. And we start to get stuff that looks maybe a little bit more like the Milky Way, so it's the end state. This is not designed to be a perfect analog of the Milky Way. And the satellite is not designed to be a perfect analog of the Sagittarius dwarf, which is currently merging into the Milky Way. It's about to punch up through the far side of the disk and probably disrupt the final time. However, despite saying this is not a perfect analog, we're going to choose a present-day snapshot that looks the most like the place where Sagittarius would be and see what happens. And so you see here the dwarf is on the far side, it's about to punch back up. Disclaimer is it's too massive compared to the Sagittarius remnant. It's not a perfect analog, but you can see at this point, we have these large-scale ridges and ripples features. They're not a perfect match to the Gaia data. And also I want to point out there's no bar in this model at this stage. It will form on later, but right now we have them. And you can look at what's going on in the simulation. And this satellite impact makes all the disequilibria features that we saw so far. So you have these ridges and ripples in radius versus azimuthal velocity. This is the simulation, this is Gaia. You have the phase spiral, this is Gaia, this is the simulation. And we also have the moving groups here, which is purely coincidental. I'm not saying that the solar neighborhood moving groups were created by a Sagittarius-like dwarf. However, people commonly use these features, so Hercules and the hat up here, to measure the bar pattern speed. You can make these even if there is no bar whatsoever. So these measurements are difficult. This was done by my undergrad, Jonas Deleo from Columbia, who's now in Madison, Wisconsin. Yeah. And so a lot of this talk is now going to form in the phase spiral and the vertical perturbation for the rest of it. And as I said, this model forms a phase spiral. If you take the little volume around what would be the sun, Sagittarius is on the dwarf is on the far side, you get this little phase spiral here, but it's not a quantitative match data. And I'm just going to do a little brief digression on how and why such spirals form, because it's important for later. And it's to do with orbital frequencies, or more accurately, the ratio between orbital frequencies. So for a star orbiting around the galaxy, right, it goes round and round, fine. It also goes in and out. You have some radial eccentricity, and it goes up and down, has some vertical eccentricity as they go around. They're not all perfect circles. And so for this little infographic from Wilmatrick's thesis, we have 3 orbits that are all pretty close to circular, but it's enough to show what's going on. You have this orangey red orbit. It's perfectly circular in XY. If you look at Z, it has some vertical excursion. And you have the green one, which is perfectly planar, but has some significant radial excursion. And then the blue, which has a bit of both, right? And so in XY space, that's fine. You're used to think of the orbital dynamics. But in Z and VZ, the place where these spirals are, you have those same kind of tracks, even though it's not a true orbit, right? This green one, which has no vertical excursion, sits right at the middle. Its Z position is 0, its VZ position, its VZ is always 0. The orange one has a little bit more vertical excursion, right? It will follow around this track in Z and VZ if it's not further perturbed. And then the blue one, which has more vertical eccentricity, goes around. And so I'm going to talk in action angle coordinates for a little bit of this. If you're collecting nemesis, you'll know what these are. If you're not, you can think of action effectively as the eccentricity, and you don't lose much of the story. But the action is effectively the area within this space, roughly. Angles are where you are on your orbital trajectory around the space, and the frequency is how fast you're going around. And the key here is that just as when, in the disk plane, stars in the center of our galaxy will orbit faster than stars in the outskirts, the same is true in this projection, where stars going round and round their little ZVZ tracks in the center will go quite quickly, and the ones further out will go more slowly. So the higher action, the further out you are, the higher your eccentricity, the lower your frequency. And this has the effect that, well, when everything is smooth and stable and you have your equilibrium distribution, you see nothing. It's fine. It doesn't matter they're going around faster in the middle. You can't tell. But when you have some distortion, when something comes by and pulls all those stars away from the disk plane, whatever it is, you will then have this ball smeared out around these tracks differently. So the more dense part is now away from the 0 point, and it will follow around here. And so again, like this bit will go around faster than the bits on the outside. And this ends up with you smearing the whole thing into this spiral as they mix back towards a new equilibrium with a different distribution. And there's this nice little movie from Adrian Price Whalen here. This is a toy example, but these are the orbital tracks in one of his Milky Way potentials. You start with a bunch of stars there, right? The ones in the middle go around faster than the ones in the outskirts. Over time, you wind up into one of these spirals because of the differences in the frequencies as a function of action. This is also a moment to point out people in different groups have a different convention of putting Z or VZ on each axis. And so it will look like some of these spirals are clockwise and some are anti-clockwise. They're all the same. They're always trailing spirals. They always phase mix in the same direction. You don't have anything leading. They're just, I don't have strong feelings on this, but some people do. And now is my chance to try and explain why you should care about these phase spirals and why you should listen to the rest of my talk. And they're a cute little interesting dynamical phenomenon, but they actually code quite a lot of information about the potential of our galaxy and about whatever perturbation has done that distortion. So there's this example from Axel Widmark, where even from this really weak spiral, which I'm willing to bet you can't see on the right, but it is in there, you can infer the strength of the gravitational potential if you know its shape. If you know nothing, it's harder. But from the way that you can see these stars go around the orbital tracks, you have the relic of like all this orbital motion. And then if you know, if you know the potential, you can then infer information about the perturbation. So as an illustration from former graduate student Stanford, sadly left the field. This is an idealized case. We have a single impact of a test particle disk, so nothing else going on, no self-gravity. You hit it, you let it ring, you generate this spiral. Well, you can track all these stars back in time to unwrap the whole thing, and you can infer the time that perturbation happened. And so in this idealized case, Elise recovers the correct time to within about 5 million years, which is great. Now, in practice, it's not quite this simple. The disk is not test particle, it has its own self-gravity. When you impact the disk moves. So the stars don't oscillate around the old midplane. The potential caused by the stars changes how they evolve. And so there is exploration of this by Larry Widrow in Queens and Tetsuo Asano, who's just moved to Barcelona, that shows nicely the effects of this. Secondly, we don't usually have such a beautiful clean spiral. Okay, the main Gaia one looks pretty good, but if you have older substructure, previous interactions, you can get things that are a lot messier. Thirdly, we think that GMCs can cause diffusion and erase spirals quicker than they fully phase mix, came from Scott Tremaine and IAS. However, we do see phase spirals everywhere, so they can't have been completely eradicated, but something is going on there. Four observations going on at the same time. I'm going to talk about that in a minute, because it's some of my work. Fifthly, stars are not a homogeneous population, right? Some have been recently born after an impact. Some have different velocity dispersions. The hotter thick disk and the cold thin disk will respond differently. And then finally, even within one volume, you actually have a superposition of lots of different phase spirals. And so this last one, however, I'm going to say is a feature and not a bug. This is actually helpful.
Sorry,
yes,
you mentioned one item which is very important, that's whether the dark matter has a core or a cusp. Because the amount of dark matter and how it responds to the perturbation depends on an unknown, at least.
That is important, and I do touch on that at the end, but you're right. So I'll answer now. There's some works that have looked at, I think from Rob Grand was the first one, where if you have your satellite come through, you create, in some dark matter theories, a big wake and the dark matter attracts you on the halo. And then that dark matter response can actually put more torque on the disk than the direct influence of the satellite in some configurations. And so I'll touch on this a little bit later on, but like depending on your model of dark matter and depending on the exact orbit and nature of your satellite and profile of the halo, that can be the dominant effect, or it can be subdominant. And we don't know which is which yet. You're absolutely right. But for the superposition, this is the Gaia data within 1 kiloparsec. We see this nice clean phase spiral. But we have stars on many different orbits, right? We have some that come from the inner galaxy, radially eccentric, visiting the solar neighborhood, spend most of the time further in. And we have the opposite, right? We have stars that spend most of the time in the outer disk, and they're just visiting us now on the inner part of the. And so you can split this local volume by angular momentum, and you'll get a bunch of different phase spirals, right? You may not be able to tell too much difference between plots next to each other, but if you go all the way from the left, you start going down, up and round. On the right, you start going up, down, and round. Like this one's obviously less whack than this one, right? You have different spirals all stacked on top of each other. This is great because they actually probe different regions of the disk if we can learn to utilize them properly. So we have this, I forgot to put the credits in Kathleen Johnston. If you have these 3 populations of stars Today they're observed around the sun, the blue, yellow, and red ones. But depending on their angular momentum, around 1 orbit ago, they would be smeared out like this. Depending on a different guiding radii, like 2 orbits ago, they'll be even further apart. And so if you're effectively getting a window, say if something had happened to the galaxy at this point in time, you have a window on it from 3 different locations in the disk, all located in the solar neighborhood today. And so this was a nice test from Cyril Gandhi that we did grad student in Columbia, now moved to postdoc perimeter in Canada. And just for a test particle simulation, we do this test. We select stars around the present day position of the sun. We split them by angular momentum. We get these different phase spirals. So like loosely wound for stars with higher angular momentum. This actually makes sense because they have lower frequencies in the outer disk. They take longer to wind up. And in the inner disk, they wind up faster. You may also be able to see slightly, depending on the projector, like this one is a lower density contrast than some of the other ones, which are more intense. So if you trace back where all these stars were at the time of impact, which we can do in the simulation, the impact was here. It's this big red blob of vertical perturbation. And so you see this red group was actually really bang on top of it. If you look at the red one, the influence was strong. This green one was further away, the influence is weaker, right? So we contain some kind of spatial information about where the perturbation may have happened if we can do this properly. And similarly to the angular momentum, you can also do this in, well, if you're a dynamicist, this is the azimuthal phase angle, which is the conjugate angle of the azimuthal action. If you're not a dynamicist, think about this is whether the stars spend more of their time ahead of the sun on its orbit or behind. So you're getting an azimuthal split around the galaxy as well as the radial one. And then you can effectively split them up into these 2D maps, even from a local volume. So I'm going to do that with the simulation I showed you earlier. Billion particle merger, phase spiral within 1 kiloparsec is here. If you go out in physical location, everything blurs together because you're stacking too much on top of each other. But if you split the local volume by angular momentum and by phase angle, you can probe what is normally a different orbital regime even from local data. And the only thing I want you to take away here is that the phase spirals are different as a function of these 2 parameters. And from that, you can make this split kind of in 2 dimensions, even from local data, where stars spend more of their time. It's not a true physical mapping, it's an orbital mapping. And yeah, this introduces radial action angle biases discussed in the papers, so I won't go over it now. But like a 1 kiloparsec volume lets you probe roughly 4.5 kiloparsecs in galactic radius and around 40 degrees in azimuth. And yet all of those phase spirals from these panels are contained within this local volume according to the solar neighborhood. Okay. However, models are not limited by such a selection function. We can look further away from the solar neighborhood. And so this very busy plot here on the right is dividing our galactic disk up into 900 1 kiloparsec bins and seeing what the phase spiral would look in all these places around the galaxy. So the 3 things I want you to take away from this are, 1, the phase spirals are ubiquitous. They're everywhere. We don't live in a special place. You expect it to just be present everywhere. Secondly, you may be able to see, depending on how close you're sat, that phase spirals next to each other are quite similar, but they're different from ones that are further away in a different part of the galaxy. However, those ones are similar to each other, right? And the other part is if you kind of squint a bit, the whole thing makes one big spiral pattern in those correlations between the different spirals. And so there are large-scale correlations with these small-scale spirals. Now, the other thing that models are not limited by is to be in a single time, like we are stuck in the Milky Way. So if you think that this is too many panels to have in a plot, I have animated it through time, and you go from 900 to about 750,000 panels. So here is the time evolution of this space. Right? In the beginning, you have nothing. All of these are these perfectly smooth, roughly spherical ZVZ planes, no perturbation, nothing's going on. Around now, the satellite goes through. You see the whole space ripple as stuff is pulled away from the midplane, and then they will wind up into these phase spirals as everything mixes back towards equilibrium. Now, it's not quite as smooth on the big screen, but you can still get what's going on. When you have the second impact, you see the whole plane ripple again as stuff is dragged away. And each time you have an impact, you have spirals on top of spirals. Everything becomes very messy, right? Until we get later on towards saying present day is around now in this model. So you see those thin spirals like far across the disk. Now, in case you don't have enough time to fully absorb that, I'm going to freeze on a couple of times. So after that first passage, we saw this ring spread out of these two-armed, pretty regular phase spirals, right? They occur mostly in the outer disk, so beyond the solar neighborhood, and they're pretty well behaved. You fast forwards to the present day for the simulation, which is imperfect. They're further in, they're one-armed, and they're messier, right? So this is more qualitatively consistent with what we see in the Gaia data around the solar neighborhood, and the outer disk has become a mess. And why am I talking about two-armed phase spirals? The Gaia is one-armed. Well, sorry, scratch that for a second, but like what is the difference between the two-armed and one-armed? Well, in this model, it's owing to the nature of the interaction. That first passage past the edge of the disk is really fast. It's almost impulsive. It like satellite flies by the outside faster than the vertical oscillation of the stars in the outer disk. They get either an energy boost or decrease depending on their vertical phase. And this introduces something called the breathing mode. So stars above and below the galactic disk are going up and down like that. Second and later passages are slower and extended, right? The satellite really sweeps under the Milky Way, it pulls the whole disk down towards it, it bends it, makes a bending mode, where stars above and below the midplane are going up and down together like that as the whole disk wobbles. And so coming back to our little cartoon that we had earlier, the bending mode on the right is what we saw before, it's the one-armed one. The breathing mode is the two-armed. So when you have your interaction, the bending mode, everything gets pulled away. The breathing mode, everything gets stretched or compressed, depending on how you want to think about it. And then they wind up in different ways, right? You have an m=1 offset that winds into a one-armed spiral. You have an m=2 pattern, which winds into a two-armed spiral. But the Gaia spiral is one-armed, right? Why am I talking about this? Well, the simulation shows a one-armed spiral on the local volume, as does Gaia. So I predicted back in 2021, this is an evolving version of this talk, that we would be able to later on see these two-armed spirals in the outer disk as relics of earlier. Because even though it is messy, if you look further out and around 15 kiloparsecs, you still see these relics of the two-armed from that first interaction. And the reason that I argue is this is interesting is it would give you a window on the first passage, potentially, of a Sagittarius-like galaxy. And then in Gaia DR3, we discovered said two-armed phase spirals. However, they were in the inner disk, which is the exact opposite of what I predicted. So you can see this is left to right, inner galaxy, the outer galaxy. Inner galaxy, you have these two-armed phase spirals here from the breathing mode, and then the bending mode in the solar neighborhood and beyond. And so that's not necessarily to say that my prediction won't still come true one day, because the area where I predicted we should see the two-armed phase spirals is somewhere towards that wall. We just can't reach it yet with present data, so it might be fine. But now we have to ask the question of, okay, well, where did the two-armed phase spirals in the inner galaxy come from? Because the picture that I just gave you with the impulsive interaction doesn't work for this. You cannot, like the inner galaxy has higher vertical frequencies than those stars, they oscillate quicker. You cannot have a satellite that goes by faster than the period of the fast stars and slower than the period of the slow stars. It doesn't work. So we need some other mechanism to explain this, or something is wrong about our intuition of where these come from again. And so another option is internal substructure. So this, it's a little fuzzy on the screen, but this is phase spirals from an isolated barred M-body spiral galaxy. In the inner disk, we have these two-armed phase spirals, but in the outer disk, there is nothing. The bar does not buckle, but it grows resonantly, and we have these spiral arms that are generally doing their thing in the disk. You take that same M-body model, you hit it with a satellite galaxy, and you reproduce qualitatively the behavior we see in Gaia data, right? So the inner disk has the two-armed phase spirals, and the outer disk gets its one-armed. And in this instance, the inner disk is just making it through a breathing motion that naturally arises from internal secular dynamics. And you see it decay in amplitude away from the center, whereas the outer disk, the one-armed phase spiral, grows in amplitude as you get further from the external perturbation. So this is what I'm proposing, that in the Gaia data, you see this transition from internally to externally induced phase spirals. And there's been a bunch of follow-up work on the internal phase spiral creation. Other groups have made these two-armed phase spirals from a slowing bar where the vertical potential changes rapidly. You can make them with spiral arms that introduce a transient breathing motion. I think in my particular case here, they're generated by the spiral arms because they correlate with the location of the spiral arms, but you can also do it with a galactic bar apparently. So I suggest that this, in the real Gaia data, you see the transition from internally to externally induced vertical disequilibrium. And I'm mostly talking about the external stuff today. And coming back to what we can learn from them, well, I showed you before Elise's little idealized tool where you can unwind one of these phase spirals and learn the interaction time. Well, we know it's not that simple. Self-gravity plays a large part, but if we just ignore all that for a second, what can we learn? Well, you can make a map of inferred impact times across the disk from my like 2D spread of phase barrels. And what you get if you do this naively is interaction time somewhere between a few 100 million years to a gig a year as a function of angular momentum. So this is from inner galaxy on the left to outer galaxy, and as a function of azimuth. And we see some kind of large-scale coherent structure-ish. Stuff that's just outside the solar neighborhood seems to infer longer ago impacts. Stuff in the inner galaxy infers more recent impacts. This cuts off before the two arms. This is just the one-armed impact scenario. There's also some kind of large-scale correlation in phase. Now, to me, I believe that there are large-scale correlated structures between these. I do not believe the inferred impact time, because we know that self-gravity changes it. There's more recent work from Tetsuo Asano suggests a large-scale delay, but it's not quite clear on how the delay changes as a function of galactic radius or properties of the halo yet, so we don't really know the answer to that one. However, various independent estimates making these kind of measurements find the same qualitative answers. You have lower values in the inner galaxy. So this is how one from these going forward. Teresa and Toa in Barcelona finds like a slight slope as you go out, and this branch of higher impact times. There's Frankel from Toronto. She goes further in. So this is the two-arm stuff, which is a little messy. But if you look at just the one-arm stuff, she has that same pattern, right? There's this spike of slightly higher times and a general trend of increase. And as showed nicely, the amplitudes of the phase barrels follow a similar thing, right? You have these bands of stronger and weaker amplitude phase barrels. And more recently, Axel Widmark's done what I think is the nicest illustration of this so far, using just proper motions for stars outside the radial velocity sample. The vertical proper motions in, so effectively mu b, can still give you most of a phase spiral, even though the middle of it is often cut out by extinction. You can kind of fill in the gaps and unwind it. So Axel made this nice map. This is the gravitational potential scaling. Makes sense. You know, you have your potential is strong in the inner galaxy. Great. It's not as competitive potential estimates as certain other choices, but it's cool that you can do this straight away from the phase barrel and that space. The winding to me is super interesting because you have these bands, right? Axel does not go as far as inferring times because he's skeptical of the methodology working, as I am as well. But the windedness, just the pitch angle of them, shows clear oscillatory patterns in these bands, right? So you have more tightly wound, more loosely wound, more tightly wound, more loosely wound, more tightly wound as you go out. These rings are again perhaps rings. Also, sorry? The contour is the map from, I think it's also Eloise Poggio's spiral arm contours for upper main sequence stars. So the original idea of Axel putting on this was to see whether these parameters inferred from the phase barrels match the spiral arms. Thank you, Masha. It's good point. And so to some extent they do, but they're not perfect, right? This inner part, you do have a good match for the spiral arm inside the solar neighborhood. The one outside, where actually we're a little bit off in pitch angle, so it goes across. You see, this is the track of that arm. So it goes to the interarm region through. So it's not a perfect match. It's unclear whether, you know, the spiral arm maps themselves are not perfect, but it's still pretty cool.
That's
It's the Radcliffe way, you think?
I'm pretty sure. I'm looking, but I'm pretty sure.
Yeah. Then we should absolutely talk about that later. That'd be great.
Yes, we will.
Yeah. And then just finally on the right, there's also this large scale coherence in the phase angle, right? So we have this blue band. Phase goes all the way from 0 to 2 pi, so it wraps around, but like you have this large scale coherent structure, similar to what we saw with Elise a few years ago, but much, much nicer with the more recent DR3 data. And so even a single impact or interaction, a single perturbation actually ends up making these bands. The next slide is easier to show that, but like this is an illustration from Kian Tavangara, grad student at Columbia, where you can kind of see there's some correlation in the pattern of these phase spirals. This is plotting spirals from a test particle simulation as a function of, again, angular momentum and phase angle, and you can see there's some kind of trends in these diagonal bands. But if Kian puts all this back on here, right, the inferred amplitude of the phase spirals, when you have your interaction, you have a large-scale dipole. But then just because of the differential rotation of the disk, this initial signal winds up into stronger and weaker amplitude bands of phase spirals, similar to what we saw from Surya Gandhi's stuff on the much earlier slide. Depending on where you are in the disk, you just felt that interaction to a different level of intensity. If you're nearby on the right side, it's strong. Again, so comparing this to axles, if you have some single impact, you see, your bands of windedness or amplitude on these kind of cadences. So it's kind of what we would expect from some large single impact, perhaps. So we come to the question, what is actually making the phase spirals after talking about X? Well, one of the leading contenders is, of course, the Sagittarius dwarf galaxy. We have this dwarf galaxy that is merging into the Milky Way on the far side now. This, when it was first discovered, was kind of presumed to be the cause. A lot of papers have looked at this, myself and other groups. So the timing is not terrible for the previous disk cross. Well, so one before disk crossing. So Sagittarius is about to punch up through the other side of the disk. It's crossed once here, and then it crossed back here a longer time ago. The timings from this interaction, punching up before going all the way around, are pretty close to what we infer once you take into account the delay from the self-gravity. However, the problem is the present-day mass of the Sagittarius remnant, as measured from internal kinematics by Eugene Vasiliev, is thought to be about 4 × 10⁸ solar masses. That is nowhere near enough to do the kind of distortion that we see in the Milky Way disk. And so either you have to have lost a lot of mass between that one before by one disk crossing, but you need a really hefty mass loss in those last couple of disk crossings in order to get the kind of level of perturbation we see. So it's not guaranteed. Some ways it fits well, some ways it fits really badly. Other options, could there be any other recent current dwarfs? Well, Udapan Banik now at the IAS basically says no. The only other one that's large enough is the Magellanic Clouds, or the LMC specifically, but if it's on that first infall, it just doesn't have time to create the ripples and the winding of those phase spirals. In the future, it will, after the distortion, the current changes to our disk start to wrap up, but we're not there yet, and everything else is too small. Could it be the galactic bar? Well, Sergei Kopskov in Germany had a paper where if the bar buckles, you get these ripples spread out across, which behave in this way. But you need it to be relatively recent buckling, and there's no other evidence in the inner galaxy of having such a recent buckling event. Non-buckling galactic bar that grows resonantly can still have a change to the vertical potential. So that is in my model. It's in this other model by Li in Shanghai. But that naturally makes the 2-armed phase spirals in the inner disk, not the 1-armed in the outer disk. Spiral structure, similarly, me and Li again find this naturally makes 2-armed phase spirals in the inner disk, but no 1-armed phase spirals in the outer disk. Could you have a stochastic bombardment by a dark matter subhalo population? That's an idea from Scott Tremaine. It shows that a lot of tiny kicks can add up to the effect of one large kick. However, based on the lambda CDM mass spectrum for dark matter subhalos, it's still dominated by things on the size of Sagittarius. So actually you kind of come back around to the same solution. However, if we're wrong about that mass spectrum or dark matter theories are different, yeah, that could be a good result. And then as we heard earlier, dark matter halo response itself can cause a larger torque than the satellite impact. So that first interaction of Sagittarius in my simulation makes a pretty decent distortion to the halo. But for my model, the satellite is still the dominant torque as it gets in. Other people's models find different things. Rob Grand's one from this paper showed that in some of the Auriga ones, you end up with a larger force from the halo distortion rather than the satellite itself. We do not know enough currently about the Milky Way halo profile or the old profile of Sagittarius to know the answer to this question, but it could be either way. And then finally, we have the problem that giant molecular clouds can actually erase the phase spirals through diffusion on the kind of timescale of around a gigayear. And the upper limit of all the phase spirals timing that is being measured is around a gigayear. So Scott's also pointing out that all these models with just the pure M-body or pure test particle, they make these thin phase spirals over a long period of time. Like mine survive in that model I showed you before for about 2.4 gigayears. He says they shouldn't exist on that timescale, but something must be replenishing them if they're being washed out. So something's still going on. So the answer is we don't know. We're not sure what the dominant effect is. We do have ideas of what we need to do to figure it out, but right now I cannot give you a solid conclusion. And at the moment, in my mind, the question is not so much what's doing it, but the question is there a single dominant cause, or is it a complex combination of all these effects, right? We know we have Sagittarius, we can see it. There are other dwarves, LMC's pulling on the halo and warp a little bit. We have a galactic bar, whether it's buckling or not. We have spiral arms. Depending on your preferred theory of dark matter, we probably have dark matter subhalos and a complex response, maybe, don't know. And we also have giant molecular clouds. We can see them, right? Like all of this is going on in the Milky Way. However, if one of these things is very, very dominant, you will still get the single pattern from that one perturber. However, if they're all in the same order of magnitude, it might actually be really hard to tell them apart. We just don't know the answer yet. So the question becomes, how can we break the degeneracy? So what most of us are looking for is this large-scale pattern across the disk. Like I showed you the result from Axel Widmark or Kian's test data, the way that this single perturbation and the properties of the phase spirals vary as a function of galactic radius and azimuth should be able to tell us whether there's a single impact point that has radiated out everywhere, or if we look a bit further and actually this is just a load of smaller, tinier arc-like features, it may imply something more random or something more stochastic. My opinion is that Axel's is starting to get far enough that I feel like there is coherent bands, which would lead towards some dominance, whatever it is. But I don't think we're quite there to be able to say for certain that that is true. The other thing that may be interesting would be to link the dynamics of the chemistry, right? If you have one of these multi-impact satellites, so Sagittarius, it's gone around multiple times, gone through. Well, in my idealized M-body models, you heat it once, stays, there's no more stars. But in the real galaxy, you have stars forming out of the thin, cold gas disk at each time. So you have different populations that will have felt different perturbations. If you have a stochastic bombardment of subhalos, you probably have this vertical perturbation growing slowly over time. But if you have a few distinct large impacts, there's going to be differences in stars with different ages. So we don't really have any perfect models for exploring this yet because such hydrodynamic simulation is very expensive, but we need them to go further, not only to account for that and the differences in the stellar populations, but also to try and model the GMC diffusion and see whether we can still do what we're getting out of the test particle and body models with these more sophisticated simulations. So I'm reaching the end of my time, but this is what I'm working on now. This is all a work in progress at this point. I don't have grand conclusions, but I've been running high resolution hydrodynamic simulations. I won't run this through, but now you just have stars, dark matter in the middle, gas, and this has a Sagittarius-like perturber coming in. This is an LMC that will arrive right at the end in an attempt to do the same kind of test that we've done before, but with the more realistic physics and star formation. And this is the very brief result that I made a plot a couple of days ago that has not informed me of anything interesting so far, so I'm gonna have to dig a bit deeper, but you can now do these splits as a function of stellar age. And so, of course, one of the things which I thought would be the case, but is proving even more annoying than I expected, was that stars that are young, so this is different age bins, this is everything, this is stars younger than a gigayear, well, they're all born pretty close to zero, so there's no phase spiral there. And then as you go up further, you do get, a larger spread of vertical actions. That's fine, vertical heating as you would expect. But I haven't had a chance to go through and do the large-scale correlation mapping that is needed to see whether you actually get any useful information out of the different stellar populations. This is where we're going in the future. We can also observe this galaxy. Now that we have the self-consistent, metallicity age information for these stars, it's easier to make such mock catalogs. And I'm very interested in doing not only the kind of mock catalogs for Gaia, but also for external, as if they were external galaxies. So we can look at the same perturbation from the inside and from the outside with a Hubble or a JWST-like catalog, which is something I've been working on recently. Again, yada, yada, stars gas behave differently, young and old stars will respond differently. So it's interesting to look at these different populations. And so this is just one of these beautiful things that was made by the FANGS team. For the same galaxy, the Hubble view in optical and UV, and the JWST view in IR. And so we can make these kind of mock Hubble or JWST images from these kind of hydrodynamic galaxy simulations. And this is where I got thoroughly distracted because I was contacted by the American Museum of Natural History to do a new Milky Way Sagittarius encounter for their new planetarium show, Encounters in the Milky Way, narrated by Pedro Pascal, which is a lot of fun to do last year, but derailed me a little bit from my science goals. However, it's resulted in ending up with a nice catalog of beautiful professional renderings of Hubble and JWST-like views for this galaxy. So it's been a nice science advantage to me, not just an outreach event, but it's been a lot of fun to do this. So yeah, if you're ever in New York, this should run for a few years. It's fun to go and watch. And just a couple of illustrations of what I will then future use it for. This is one of the optical renderings, and you can see from this galaxy, you have the kind of waves in the edge on disk that you would expect to see. So you can compare how would Gaia see this wave versus how would Hubble or JWST see this wave in something external and link it all together. But I don't have any useful science results for you at this time. You also get the bubbles and filaments, which is hopefully of interest to Alyssa and group. So this is one of the JWST renderings. Again, same galaxy, slightly different time step, and you get all the bubbles and and stuff that evolve over time. So this is where we're hoping to go in the future. But for now, I think I will leave you with just an animation of this and close and take questions. So this looks nicer on a dome because it's supposed to be, a hemisphere over you, but it's still it's still nice. Oh, it's not working at all on the Zoom. It looks great on my laptop. Oh, it's cool. Little jittery, but it's fine. Yeah, you saw it as well.
I saw it again last week, yeah,
How'd you like it the second time too?
it was better the second.
Yeah, thank you very much, everyone. That's the talk. Hopefully, if I get to give another Colloquium in years' time, I'll be able to actually conclusively answer where the ripples come from, but we still don't know yet. Yes, go ahead.
So I was wondering, I think you started to touch on this in your later view graph last month. But if you have a number of these causes and they're all equally likely, and a number of them are likely to be operating at the same time, it wouldn't likely add in coherence, right? And so why you would have, how would you get these ripples then if these things are interfering with each other?
So the ripple. So again, this is we don't conclusively know the answer to your question. My feeling is like the ripples are very likely to have come from certain factors. So in fact, Sagittarius is a really good collaborators. Thank you. Is a really good potential explanation for the large-scale radial velocity ripples. There's a model that I will try and work it by talk in the future, but from Johannes de Leer, former undergrad, if you have a Milky Way galaxy, you throw an LMC at it, you get a large-scale dipole, slightly like the warp, but not enough. For a Sagittarius, you get these thin bands, and actually the arcs of radial velocity are very well matched to what we get from a well-tailored orbit of Sagittarius. However, this model does not make phase spirals that look anything like what we see in reality. So my impression is like some of these things we will be able to extract, but I think there are multiple things going on top of each other. And we need, I'm a simulator, so I always say this, we need simulations that have the combination of everything and to varying degrees of mass and amplitude to see whether we can pull it all apart. Because like in this example, this model actually does a really nice job of matching some things and completely fails on matching other things. Whereas naively, I would have expected if they all came from the same perturbation, that if we match the ripples, we should also match the phase spirals. And that doesn't appear to be the case.
Yeah, so you talked about the hydro gas simulations towards the end. Do you actually make molecular clouds, GMCs? Can you verify Tremaine's prediction that they will tap down?
Not in this one. So we don't in this example galaxy. We want to work towards that for the future because it will be important. But sorry, I skipped over. This is our first attempt at doing hydro, so it'll be good for the stellar populations. It won't hit the proper modeling of the GMPs. Okay. Yeah.
It's doable.
It should be doable in the future. We can do it, but we can't do it for the resolution necessary to do everything else. That's the problem, right? So like we need that, but we can't do it right now, which is why I haven't done it. But like in the future, it's important. We'll have to do some kind of hybrid thing in the middle to test the diffusion, perhaps on. Like we were thinking about how to do it. Like we run our hydro in certain ways, and then perhaps we take a smaller box volume over a smaller period of time, add manual diffusion, and see what happens to the orbit. But like it's not clear exactly how we do.
Awesome talk. So whether warp would show up in the spiral size of radiation and related to this, whether tracks of halo can produce.
Track to halo absolutely can produce.
That might fall down.
Yeah, it's a couple of different points. So like the warp and the phase spirals, they don't have to perfectly correlate because like the phase spirals effectively are, in the simplest case, wrapping around the midplane. So if you have the whole disk warp, they just wrap around the warp. So it doesn't necessarily break or make them. However, the triaxial halo can make both, depending on the exact orientation. It could be responsible for everything. So it's one of it might even be my favored theory that Sagittarius is responsible for everything, but a lot of it comes from the fact gave a lot of triaxiality and halo torque response. Because like LMC broadly puts the warp in the right direction, but there's plenty of things it misses. It doesn't make the amplitude strong enough, the lane of nodes is wrong, the precession is wrong. It's like the LMC is probably adding to it. It's on the right orbital plane to perfectly correlate. It doesn't do it by itself. Like a lot of groups are finding that. Jesse Han, who was here, has a really nice explanation from the halo. And so I think that's a big part of it. Whether that triaxiality came from GSE or Sag. Sag is also pretty big. It should do stuff like that. So.
Any other questions? No,
I guess.
Yeah.
You also you didn't talk about the LMC and SMC mushroom. So is it because you're just coming and the timing is not right?
Yeah, that's right. So the LMC, like we know, we have the measurements of like there's a reflex motion, there's a lurch, it pulls the disc up a little bit on one side, regardless of what else is happening. But there's not enough time for that to then mix into these phase spirals. You will have the largest influence when you effectively either cross disc or have pericenter, depending on exact morphology. And there's not enough time to do it. There are some theories, of course, that LMC is on, second passage. But if you look at those, it looks like they're from so long ago that these would have then all mixed away. So there's no, to my knowledge, models where there's a recent enough impact to account for the phase spirals. So I think we can discount that one. But it's probably part of the global picture of the vertical disequilibrium. Actually, this is a nice. This is radial, but it's fine. Like you get the large scale mean shift field from the LMC, whereas Sag has had enough time for those things to start to wind. Because the LMC is just now making the kind of large dipole scale across the disk.
And the wake and dark matter halo is it also like?
I think it's the same thing. I haven't specifically investigated LMC's wake on this one, but my intuition is it's the same, and there just hasn't been enough time to do the kind of like rippling phase spiral stuff that we're looking at. Yeah.
Any last questions? Yeah.
The mass of the Sagittarius doesn't match what you require, but it's the mass estimated from like the stellar mass, halo mass relation.
So the present day remnant mass is estimated from the internal kinematics of the remnant. So there's certainly some wiggle room on that. We don't know it for certain, but I think the error bars are not large enough to get us up to the kind of scale that I find you need to do these ripples. However, that's at the present day, right? You've had a couple of impact points, you have had more stripping, and we can see it in the stream. And so initial mass estimates of Sagittarius actually they're really wide range depending on who you ask, anywhere from like 10 to the 9 to 10 to the 11. I think it's probably mid to high 10 to the 10s because Sagittarius is remnant is shockingly metal rich. It's like more metal rich than the LMC. So it must have been reasonably large. Like there's scatter in the mass metallicity relation in these kind of dwarfs, but it can't have been super tiny to have formed the kind of stellar populations that we see in the remnant. So it has to have lost a bunch of that mass over time. And so those earlier impacts can be significant, even if the remnant today is like nothing. Eugene Vasiliev's model is probably my favorite one. It seems to suggest that the next disk crossing in a few tens of millions of years is going to shred that remnant completely and it'll be gone. But yeah.
Great. Let's thank Jason again. He'll be around tomorrow. There's a sign-up sheet online if you want to meet with him, and I'll head upstairs for lunch. Thanks, everybody.